Hello, everyone. Welcome to the April 14th edition of Math 371. Reminder that you have online homework due on Friday. This should cover some stuff that was on the midterm as well as some material you're learning today. So today the goal is to get a little bit better understanding of the action where you send a vector to A times that vector. Now, you might think you know how this works, and you do, but you can actually often see this, how the matrix affects the vector um, on a graph in some very easy ways. So there are certain special vectors that multiplying the vector by the matrix gives us a very special action. So let's take a look. Let's do an example where we have the matrix 1, 2, 1, 0, and we have the vector u and the vector v. And let's look at the matrix A times the vector u, and what this should give us, it should give us the vector 1, negative 1. So observe that A times u was negative u. Let's also look at A times v. What we get is 4, 2, which is 2 times v. So A times v is 2v. So if we draw a little graph, 1, 2, 3, 1, 2, 3, 1, 2, 3. If this is my vector u, this is my vector A times u. If this is my vector v, this is my vector A times v. So we see that in the case of u, A is flipping the vector u around. In the case of the vector v, A is stretching out the vector v. So in this chapter, we're going to study equations such as A times a vector is negative that vector, A times a vector is 2 times that vector, and maybe it's 4 times that vector. So these are special vectors where when you send the vector to A times the vector, these vectors are scalar multiples of the original vector. And we have special names for these vectors. They're called eigenvectors. They must be non-zero. And when I multiply the vector by the matrix, I get a scalar multiple of the vector. And we call such a scalar an eigenvalue. E.g., there is a non-trivial solution to ax equals lambda times x. Such an x is called an eigenvector corresponding to lambda. All right, let's answer a question. Is the vector 1, 4 an eigenvector of this matrix? Well, there's only one way to find out. Let's multiply it. Should get a 1 and a, let's see, that's -3 plus 32, 29. So no, not an eigenvector. Because the vector in blue is not a scalar multiple of the vector I've circled in green. Let's try a different example. Is this vector an eigenvector of this matrix? I want you to try this one in your notes before I show you the answer. Okay, now you've had a chance. Let's multiply it out and see what happens. Let's see, that's 12 minus 21 plus 9 minus 16 plus 15 plus 1. And 8 minus 12 plus 4. And I believe what we get is 0, 0, 0. Yes, this actually is an eigenvector. What's the eigenvalue? You probably guessed it. It's lambda equals 0. All right, so let's flip the question around and let's ask the following. Is 2 an eigenvalue of this matrix? Well, let's assume so and then work from there. So can we find a vector where I multiply it by this matrix and I get 2 times that vector? Well, on the left-hand side, I get 3x plus 2y, and 3x plus 8y is 2x and 2y. So I'm trying to solve 3x plus 2y is 2x, and 3x plus 8y is 2y. So this tells me that x plus 2y is 0, and this tells me that 3x plus 6y is 0. Okay, so these are the same things. These are the same equations. So all we need to know is that x is -2y. So let's just pick y is 1 and x is -2 and see what happens. So that would mean our vector was this vector right here. Our matrix was this. And if I multiply it out, I get -6 plus 2, -6 plus 8 is -4, 2, which is 2 times our original vector. So yes, 2 is an eigenvalue of our matrix. All right. So although we just used row reductions, essentially, to find an eigenvector, it cannot actually be used to find the eigenvalues. An echelon form of the matrix does not display the eigenvalues of A. So how do we find the eigenvalues of lambda? How do we find the eigenvalues? So we're going to go through a little bit of a process and identify how we can find them. So we need to find real numbers so that we can solve this equation. So this equation is the same as this equation, where I is the identity matrix. So let's subtract, and we find that this equation must equal the zero vector, which tells us that A minus lambda I times X must be the zero vector, which tells us that this matrix must have a non-trivial solution. That's what we need to find the eigenvector. Furthermore, the null space of this new matrix is called the eigenspace of A, corresponding to lambda. The eigenspace is the zero vector and all the eigenvectors that correspond to lambda. So let's do the following. Let's find a basis for the eigenspace corresponding to lambda for the following matrices. So I'm going to do one of them and then you'll do the other. Okay. So let's have A equal to 5, 0, 2, 1, and have lambda equal to 1 and 5. So let's do lambda equals 1 first. So that's the matrix A minus 1 times the identity. So that's 5, 0, 2, 1 minus 1, 0, 0, 1 is 4, 0, 2, 0. And so what that's telling me is the solutions are x equals 0 and y is free. So this should say that the eigenspace corresponding to lambda equals 1 is the span of this one vector. So let's take a look. If I multiply my matrix times any vector 0y, I get 0y. So that works. Let's now do lambda equals 5. So if I look at my matrix minus 5 times the identity, I get 0, 0, 2, negative 4. So this tells me that 2x minus 4y is 0, shows me that x equals 2y, where y is free. So this should tell me that the eigenspace is equal to the span of 1, 2, 1. So let's take my matrix times 2, 1, and I get, let's see, 10 and 5, which is 5 times the original. So that tells me that the span is correct. So now it's your turn. You want to find the eigenspace of the matrix B corresponding to lambda equals 3. Good luck. Okay. So now we're going to see if we can find the eigenvalues for a matrix. Recall, an eigenvalue is one where a minus lambda I has a free variable. Okay, so let's do an example. Let's do it with the matrix 1, 9, 0, negative 1. So I notice that if I subtract 1 times the identity, I get 0, 9, 0, negative 2. This is a free variable. Therefore, this tells us lambda equals 1 is a possible eigenvalue. And if I subtract off negative 1 times the identity, I get 2, 9, 0, 0. This also has a free variable. So this tells us that lambda equals negative 1 is an eigenvalue. Those are the eigenvalues of that matrix. Now I want you to determine the eigenvalues of this matrix. There should be 3 of them. So go ahead and figure that out. What pattern did you notice? Well, you probably noticed that the eigenvalues were the entries in the diagonal. But that was because the matrices were triangular. And that's actually a theorem. The eigenvalues of a triangular matrix are the entries on its main diagonal. Okay. All right, so that concludes section 5.1, and we're going to talk a little bit about 5.2 today, which we will continue with next time. So in section 5.1, we've just introduced the concept of an eigenvalue and an eigenvector. So if one knows the eigenvalues, it's not too hard to find the eigenvectors. So knowing eigenvalues tells us that finding the eigenvectors is easy. It's just row reduction. However, how can we find the eigenvalues? So let's go back through what we know. Suppose that lambda is an eigenvalue of a matrix A. This tells us that AX equals lambda X as a non-trivial solution. And that told us that A minus lambda times the identity times X equals the zero vector as a non-trivial solution. So what do we know about matrices that have a non-trivial solution? Well, this tells us that the null space of A minus lambda I is non-trivial. That means the null space has more than just the zero vector. And what does that tell us about the determinant of this matrix? It must equal 0. So you're actually going to get an algebraic equation, a polynomial, that you're going to be able to solve to find the eigenvalues. So let's do an example. Let's compute the determinant of A minus lambda I, where lambda is a variable, for A equals this matrix right here. Okay. And so what we get is, well, we get A minus lambda I is 2772 minus lambda 0, lambda 0. So we're getting 2 minus lambda, 7, 7, 2 minus lambda. And we take the determinant, and we get 2 minus lambda times 2 minus lambda minus 7 times 7, which is 4 minus 4 lambda plus lambda squared minus 49, which is lambda squared minus 4 lambda minus 45. And it's not so hard to figure out that this factors as lambda minus 9 times lambda plus 5, which tells us the only values of lambda that work are 9 and negative 5. So these are the eigenvalues of A. So as a problem for you guys, I want you to find the eigenspace corresponding to lambda equals 9 and lambda equals negative 5. So find the two eigenspaces for those two eigenvalues. So before we do too many examples with computing eigenvectors, it's important to remember the following theorem, or remark really. Suppose A is an n by n matrix, and U is any echelon form of A obtained by only using row replacements and row interchange. That is, no scaling allowed. Then, if R is the number of row interchanges, this tells us that the determinant of A is negative 1 to the R times the product of pivots in U. This happens when A is invertible, and it's 0 when A is not invertible. Okay, so this is a formula that lets us know what's the determinant of my matrix A compared to a echelon form where I only used row interchange and row replacements. So this leads us to a theorem which says if A is an n by n matrix, then A is invertible if and only if the number 0 is not an eigenvalue of A, and which is equivalent to the determinant of A is non-zero. So we already knew that A was invertible if and only if the determinant of A was non-zero. So now we just need to know that the determinant of A being non-zero is the same as the number 0 not being an eigenvalue of A. Well, when I look at, so let's look at this equation where lambda is 0. This lambda 0 is an eigenvalue if and only if the determinant of A minus 0 times the identity is 0, which happens if and only if the determinant of A is 0. And thus we see that 0 being an eigenvalue is equivalent to the matrix having a 0 determinant. All right, so the determinant we described earlier today is related to the characteristic equation of a matrix. And it's related to a new definition that we need to know. So the characteristic equation is the equation you get when you take the determinant of A minus lambda I equal to 0. This is actually a polynomial of degree n, called the characteristic polynomial. So the characteristic polynomial is what you get when you take the determinant of A minus lambda I, and when you set it equal to 0, it's called the characteristic equation. So let's do an example so you can kind of see how things work. So find the characteristic equation of the matrix A with this. All right, well, that's not that hard to do. So we take the determinant of A minus lambda I, which is the determinant of this very long matrix to write down, which is equal to the determinant of 4 minus lambda, negative 7, 0, 2, 0, 3 minus lambda, and it's the triangular matrix. So the characteristic polynomial is just the product of entries in the diagonal, and the characteristic equation is when you set this equal to 0. So observe that the eigenvalue 3 appears twice as a factor of the characteristic polynomial. Okay. In this case, we say that 3 has multiplicity 2. In general, algebraic multiplicity of an eigenvalue is its multiplicity as a root of the characteristic equation. So one thing you should know is every degree n polynomial has n roots. It's counting multiplicities over the complex numbers. This is called the fundamental theorem of algebra. And you can learn about it in complex variables in fall 2020. All right, let me know if you have any questions, and we'll talk to you next time.